Well, officially welcome to Stephen, and thanks for finding time to speak to us. And going to talk on socio-spatial networks. Over to you, Stephen.
Thanks, Dennis, and thanks to the rest of the organisers of this for giving me the opportunity to speak today. I've been trying to do a little bit of editing as I've listened to other talks this morning, so I hope there's a few different things in here. I can't see the chat as we go, so I'll try and leave room for questions at the end. But if I do say something that just glaringly needs correcting or clarifying, especially if you're a colleague that I've known for a while, please, or anyone else, just jump in and stop me. Presenting on Zoom is a kind of unique thing. So what I'm going to do, hopefully over the next 20 or so minutes, is just explain how this talk is motivated by the current COVID-19 pandemic. Very briefly show an old example of a socio-spatial network that we made for smallpox and that I created some code for a while ago. And then I'll go on to spend kind of the meat of the talk looking at one specific project it's current. It's just gone up as a revised preprint onto bioRxiv about how certain properties of socio-spatial networks can lead to non-standard epidemics. So referencing back to an earlier talk this morning, how we'll get curves that wouldn't be well estimated by a simple SEIR model. And I'll try and explain how the network structure feeds through to give these non-standard epidemic dynamics. And then at the end, hopefully we'll have time for some discussion, or I can just merge into the general discussion afterwards. So those are the 4 parts for the next few minutes. So before this, we're not talking about a sexually transmitted infection where the mechanism for transmission and the contact for transmission is really clearly defined. STI networks can be difficult to describe because people getting the accurate information is difficult, but they have a very precisely defined transmission event. What I want to talk about just for a second is that respiratory infections don't have quite as clearly defined a transmission event. So the top left of this slide shows a flu epidemic curve from 2009. And we know that it's transmitted from person to person. We know the mechanisms are aerosol or respiratory droplet. We know lots of things about flu that we've now learned about COVID-19. And this transmission produces epidemics, and we understand some of the underlying mechanisms for those epidemics. And the picture on the top right, that's people sneeze, droplets get in the air. That's how flu gets around, and that's how COVID gets around. Then bottom right, you can see this network diagram of kind of flight paths and connectivity around Europe. So we do understand the kind of network of respiratory transmission at large scales. So we can kind of look at flight volumes, we can look at incidence in one place, incidence in another, and we can kind of estimate how quickly respiratory pathogens will move over long distances because they've got to travel with people. And the final picture in the kind of bottom left, if we're going around in a clockwise, is a lecture theatre, which is how we used to give presentations. And obviously right now, no one on this call has any high risk of getting infected by me if I was COVID positive. But if we were in a lecture theatre, like the picture in the bottom left, it'd be really difficult to know for sure how much more likely someone in the front row was to be infected by me than someone in the back row if I were infectious. So the social contacts that are actually directly relevant for respiratory pathogens are much more difficult to define than for other infections. I just wanted to kind of say that up front. But we do know that social networks exist, and we know that it travels from person to person based on face-to-face contact most of the time. So this slide is taken from a paper that appeared during the response by the Fraser Group in Oxford. It's Ferrati et al. From Science. And this is one of the pieces of work that's motivated the interest in contact tracing as a way to reduce the reproduction number for COVID. And the point they're making on this slide is very straightforward. We understand, if you look at the top row, the different contexts where transmission may occur. And if we had really good fast contact tracing on the bottom part of the slide, they show how people could be isolated and how you could reduce the average number of onward transmissions if we had very good contact tracing. And this is implicit in this is the existence of a contact network over which we could contact trace. So, and moving forward, that's going to be a major part of our thinking and the scientific questioning of the response all over, and especially in the UK. And then slightly nervous even about the next slide. And we will be using models to look at this. So I'm just putting up, it's not the first time this morning, an example output from the individual base model from Imperial College. This is a code base developed primarily by Neil Ferguson and a team over a number of years. And this type of approach is being used to look at specific intervention options. This report doesn't deal with contact tracing, but those features are also included in these large code bases. And there's, as has already been mentioned today, it's difficult to completely disentangle exactly how these things are implemented in any one set of code. And I think everyone would agree that we need multiple tools and maybe even multiple kind of theoretical approaches to look at the general question of the interaction of a disease transmission process on a contact network with some kind of case-based intervention. So to kind of try and wrap it up, the motivation into just very specific questions that we're going to need to try to answer in the next few weeks and months. We want to know how effective is contact tracing actually being with the app or without the app in the other guises that it will be used. We want to understand how clusters should be investigated, workplaces, schools, other settings, how we should prioritize them and how effective those cluster investigations are being at reducing transmission. And I'm not going to try and answer those today. These are motivating the more kind of detailed results that I'm going to give. And then I think that does motivate a kind of independent need for very good socio-spatial networks. And so by a socio-spatial network, I'll give a narrow definition for this talk. It's having a representation of where people live, so that where they sleep each night is their location in space. And then people that they contact, individuals they contact through either school or workplace or some other way, they are linked by an arc. So people live at a place in a household, they're a node, and then the people that they contact are on the other end of an arc. And if you've got contacts between people, that's a social network. And if each node is located in space, then it's a I'm going to call that a socio-spatial network. And I think that there's a lot of need for, there's some interesting questions that we can try to answer, and we need to generate really good versions of these. Okay, so very quickly, this is motivated by what is kind of, sorry, I've now realized that I have, I was trying to look at the time, but I realized I've obviously, because I'm on desktop sharing. So just to kind of flash up an example from 2006, when it was in the early 2000s, people were actually worried about deliberate release of smallpox. The general conclusion was that we didn't need to worry about that for the reasons that we'd gotten rid of smallpox, were the reasons why it would be straightforward to, not straightforward, but why it was unlikely we'd have very large outbreaks of smallpox if it were to reemerge for any reason. But in the course of thinking about that, we did look at large spatial models with a social network overlaid on them and with a contact tracing process. And this slide shows how a kind of baseline for how smallpox may have spread in the UK. And although the colors look a little bit scary, the bottom line from this slide is that even in our kind of most pessimistic scenarios, smallpox would have spread really slowly with relatively low incidence pretty much everywhere, even if it wasn't responded to. And what we went on to show with this is the contact tracing and isolation would be extremely effective at controlling smallpox because there was such a long time from infection to the beginning of infectiousness. So that's the kind of that's the example that I'm going to build on for the rest of the talk. So jumping forward now, and this is the picture here is not me if you're not looking at the screen. That's David Hoare, who's worked on this in our group and has done a fantastic job. So I want to give him credit before I dive into the details of this current paper. And for this section, I want to get more into some of kind of the interesting disease dynamic science that we can get from studying socio-spatial networks. The first one is that exponential growth, which is a feature of many different epidemic models, may not be common under some conditions. And it's possible that those conditions might be present in the UK at the present time, although certainly not guaranteed. I'll talk a little bit about how the absence of exponential growth means that the reproduction number is not always well defined. And then I'll move on to look at some specific networks where contacts are made only very locally and long distance contacts are very rare, and talk about measures of clustering on those networks. So and I'll explain clustering as we go through it. And then as a kind of general point, what I'd like to flag here is a specific example of an opportunity for novel algorithms. There's a bit of this work that is just figuring out how to create a network that's representative of what you know about how people travel and what you know about where people live. And it's a fairly tricky computational task. And I just want to flag that in these next few slides. And so this is, as I've said, that's the reference on bioRxiv for the results in this section. And all of the code, all the results I'm going to talk about are immediately reproducible from this repository, which is public. And there should be, there should also be a Zenodo kind of release of the code in the preprints. If it's not actually in the preprint and it's not obvious from the current version of the code, then please email me if you do want to look at it, and I can give you the Zenodo link for the bioRxiv preprint. So what kind of more specifically, what is the network model that this is going to be based on? And so we assume that we have good knowledge of the population density for any 5 kilometer by 5 kilometer grid, how many people live in that grid. And we assume that we know that for both households and for workplaces or schools, or, you know, these are contexts where you meet the same people and you create social links. And if we want to do that for the whole of the UK or for some kind of small population, we can make a model where we just randomly assign we assign workplaces according to their known density. We assign households according to their known density, and then we randomly assign people from households to workplaces. But that's not much use. That will give you exactly the same dynamics as SEIR, and when you run it, it won't give the realistic spatial dynamics. You won't see that propagation through space that you saw that was on the smallpox example. So the way this code works is that we've got a specific implementation of the Metropolis Hastings algorithm that you need to run for a long time on a large population, and it will go through. I hope you can see my pointer. I think you normally can with Zoom. So what this algorithm does is it goes through every assignment. These are households, these are workplaces, and it goes through every assignment from some person in a household to a workplace, and then proposes that they move to a different workplace, and then sees if you move that person from one workplace to another, does their new journey to work, is that more consistent with what we know about the patterns of how people travel to work than their previous journey to work? And if it is more consistent according to the precise accept reject of Metropolis Hastings, then probabilistically, then we move them. And if it's not with the accept reject condition, then we leave them where they were, and we just run that accept reject more and more time until we obtain a distribution, a stable distribution of people's journey to work. And the functional form that we use to do that follows this, the formula on the screen at the moment. So here, the kernel is a function of the distance between the person and the workplace divided by some offset and then raised to a power alpha. In this work, the offset part of this isn't really important. You can imagine that your propensity to travel any given distance to go to work is proportional to 1 over the distance raised to the power alpha. So here, the larger alpha is, the less likely you are to travel, and the smaller alpha is, the less likely you are to travel longer distances, and the smaller alpha is, then the more likely you are to travel. So you run the algorithm for a long time, and then once you've got a stable set of distributions, dissolve the workplaces and just link up. So if this person is connected through here to this person, then dissolve the workplace and just replace it with a link. So we get left with a unipartite network of households and links between them. At the moment, there's only one type of workplace and one type of household, but in general, there's no reason that workplaces can't be done for different age groups or different individual types, and networks generate and repeatedly, the algorithm run repeatedly to generate networks for lots of different contexts. And this is just to flag that the details of the algorithm that we use for that are given in pseudocode, as well as in the actual Git repo in that old paper. So the example that we use this on, this is a pre-COVID example, was actually a population of 1 million people living in and near to Monrovia in West Africa, because the motivating example was actually dynamics that we saw for the Ebola outbreak. And these charts show the distance distributions between individuals and their workplaces for the different powers of alpha. So when alpha is equal to 0, the distance doesn't make any difference at all, and it's just a random allocation. The reason it doesn't look uniform is because the population density is not uniform. So the location of workplaces and the location of homes gives you a, if you have random allocation, it results in this set of journeys. And then as you increase alpha, you're making it less likely that people travel longer distances, so you're making things be much more local. So therefore you get a higher frequency of shorter journeys, and then increasingly more so for even higher values of alpha. Note that there's a massive difference between these two powers, and there is a difference on here, but it's not immediately obvious to the eye on these frequency plots, but that's a much higher value of alpha in the kind of range of values that we use. So the next section is just going to kind of go through, going to have to just check time again. Okay, keep an eye on that. So I'm going to try and make 2 points in these next sections before I kind of wrap up and go to discussion. So the first one is about exponential growth. And we had a meeting a few years ago, and we had a spatial subgroup, and we had lots of fantastic discussions about R0 and exponential growth. And this kind of reflects back a little bit to those. So this is a definite follow-on from previous Newton Institute interactions. So in general, if you just look at raw incidence, and these schematics show raw incidence, it's not immediately obvious whether one curve is exponential growth or it's not. But as I'm sure every single person on this call, that's fine, we just plot incidence on a log scale. And if we get a straight line, then we've got exponential growth. And if we get something that's not straight, then it's not exponential growth. So that's one way to see whether we're in a kind of an exponential regime. Another way of thinking about that is that the gradient of the line of the exponential line is constant. So that's just saying the same thing, but looking at the derivative rather than the linearity or the absence of curve. And then in this framework, we have a third way that we can think about exponential growth, because this is an individual-based model. So we can extract exactly who infects who, because we're simulating the epidemic spreading. So we know generation 0, those were the seeds that we fed in. We know generation 1 and we know generation 2. In real life, you very, very rarely know that. In theory, with lots of genotyping, we could maybe do that for an epidemic one day. But that means that we can look at the number of people, the ratio of the number of people in the second generation compared to the number of people in the first generation. So this is the second generation, and this is the ratio of people in the second generation compared to the ratio in the first generation. And that, if you think more generally for renewal processes, that is actually the definition of an exponential process, is that it renews with exactly the same ratio each time. So we can directly observe renewal because we're observing generations from the code. And if you don't have constant ratios between generations, again, then it's not an exponential regime. So what we've done with this Ebola-like epidemic in West Africa, with varying degrees of locality, if you like. So alpha equals 0 is mass action, no space really. Alpha equals 3 is kind of quite typical, or slightly more local interactions than random. And then alpha equals 6 is extremely random, people not moving far at all. So those are the 3 columns. And then we can look at incidence in these different ways and assess the degree of the duration of exponential growth and kind of what the values of R0 might be. So I'll speed up a little bit. Here's the incidence plotted. There's incidence on a linear scale, incidence on a log scale, where it kind of looks exponential-like, although it's kind of hard to tell by eye on the right-hand side. This is the gradient of the log of incidence, where there's a lot of noise, obviously because there's noise at the beginning of the process here, but the duration of the flat gradient is definitely going down. And then this is the generational observation. So is it definitely renewal? And there's a couple of important features on here. The first one is it takes a while to kind of reach its eigenstate, if you like. And I know Peter Trapman's on the phone here, and we've given Peter lots of credit in the preprint for kind of defining this little plateau here as the true R0 for these network models. So it's his R sub star that we're claiming as R0 there, but that really doesn't exist that much when you move up to alpha equals 3. It's still there, and then when you move to alpha equals 6, it's just not there. This is not the first time it's been observed in network models by any sense, but there isn't a period for which R0 is well defined. So can we delve a little bit into the properties of the network using kind of more traditional network science ideas, and see whether we can kind of generalize a little bit as to what's going on here. What are the features of the network that are restricting, that are generating these non-typical dynamics? And this is a little bit more technical, and but I think it will be of interest to quite a few people on the call. So the degree distribution is just how many friends do I have? The average, it's the distribution of the number of contacts that somebody makes. The classic clustering coefficient is how many of my friends know each other. So, and it's a measure of how much the network closes in on itself at that first opportunity. So it's just a measure of friends of friends. There's been a lot of work on that. And then what we're going to look at is how the alpha affects these. And to do that, we need to generalize the clustering coefficient to higher orders. So what that essentially does is this idea of my friends, how many of my friends know each other, just gets repeated. But rather than using actual friends, what we say is for say an order 3 clustering, we'll go to everybody that's either 1, 2, or 3 away, and then we'll delete all of those internal links, and we'll just pretend that 1, 2, or 3 is the same as 1 link, and we'll say how many of those we're also clustering. So that's an order 3 clustering, and order 4 clustering is higher than that and higher than that. There are a lot of similar metrics in the network literature, but there's a little bit of variation in them as well. So we're very precise about what we've done in the preprint. And that suggests, when you look at the behavior of those clustering coefficients if you look at the behavior of the clustering coefficients for different distance powers, so for different degrees of locality, where it's mass action on the left here and really strong spatial clustering on the right, then what you see is that the straightforward clustering is completely unaffected, as you'd expect. It's kind of it actually is by definition in the model. And then even the second order clustering doesn't make any difference as you go up. Third order clustering, you see a slight increase in clustering when alpha goes past 2, 3, 4. But then fourth order clustering, you see this massive increase in the way the network folds back in on itself at 4 links as you increase the power of alpha. And if you go to higher order networks, it's obviously stronger. And so we see that very strong impact of alpha on clustering coefficients from 4. And then the chart on the right is a slightly dense way of saying, well, does that make any difference to the actual properties of the epidemic? And so what we're plotting on the y-axis here is the peak size of the epidemic divided by the final size. We noticed that it was apparently kind of it was kind of behaving in a fairly constrained way for some circumstances. So we explain more about it in the paper. So what we've done is we've looked at all these same kind of sets of parameter values here and we've looked at the relationship between the moments for different powers of alpha and different values for this ratio. And so, for example, we've looked at whether first order clustering appears to affect peak final size when that's kind of the only thing that is changing. And you can see these are completely vertical here. So as you go through all the different powers of alpha, which are the numbers here, so that's alpha 1, alpha 2, alpha 3, alpha 4, it's changing the relationship in a perfectly kind of linear way whilst keeping the value of that clustering coefficient constant. But as you look at the higher values for the clustering coefficient, you see that they become more and more influential, even across different powers of alpha, until you're getting this very, very strong relationship between the properties of the fourth order clustering across a wide range of alpha in how it affects this kind of summary statistic for epidemics. So I'll move on. That's possibly a bit dense to squeeze into the kind of wide-ranging talk. But I hope that I've established exponential growth may not be common under some conditions that might be interesting. Higher order clustering can explain that in the bipartite framework. It's a unipartite network, but a bipartite framework of households and workplaces that we've used, and that this general space is an opportunity for some kind of cool novel algorithms. And that was the end of the result. I have some suggestions for discussion, but I'm just going to put those up on the screen and stop because I have used all of my time and we're going into discussion anyway. So I will just put those up on the screen and I'll stop there and take any questions. Thank you very much.
Well, first, are there any immediate specific questions on Stephen's presentation? Which many thanks.
I have one. I'll ask one. It's Deirdre. Hi, Stephen.
Hey, Deirdre, how are you? I'm
good. I love your shed. This is a great talk. Lots of lovely stuff in it. Thank you. So what's, for people who are not epidemiological modelers, like there's a lot of detail about networks in there, but how well do we know about networks and what are our best? It's an obvious question, sorry. Where are the best data streams for that kind of information now?
So for we've tried really hard over the years. We've got some good stuff from Fluescape, the spatial distribution in China, but the bottom line is that the best data that exists must now be from the Isle of Wight. They've got working Bluetooth links between phones with a 30% penetration into a population of 140,000. So we've never had anything like that before. So there does now exist a biased and not representative 30% sample of a social network in a closed population. That's got to be it. Yeah.
Okay. Well, I think we'd be nice. There's lots to discuss, so let's have 20 minutes of breakouts and then.
There are still 2 people with raised hands at least. So
okay, that's the trouble with not being able to see them.
Adam, and perhaps Adam can.
Okay, thanks. Yeah, great talk and I've got lots of questions, but I'll focus on one. Your point about I think it's a really kind of good one, and the kind of what are we actually trying to capture in terms of growth? I mean, in terms of evaluating interventions, a lot of people are looking at kind of changes in the reproduction number. Do you feel of kind of the different metrics you're presenting, there's probably a better one or a better combination we could be using?
I think that if we're in a regime that's close to RT equals 1, and there's an interaction of household saturation and kind of infrequent between household contacts, I don't know there's a really obvious replacement for R, and I think that maybe what we need is really clean, parsimonious simulation models that with no more detail in at all than they absolutely need to try and evaluate further disruptions to either household or between household. So I think I don't know that there's a really good replacement, but that doesn't necessarily mean we have to absolutely stick with it. That maybe we should be, specking out some really clean household models where we can test the potential contribution of different interventions. Over.
Yeah, cheers. That's a good idea.
A quick comment on that, Steve, would be, I mean, as I'm sure you know, in a completely spatial model with, let's say, just nearest neighbor spread, then basically R is always, if the thing is above threshold, the thing R is essentially going to be 1. So you can't really tell how good it is at spreading. So, if it's spreading out as a sort of circumference of a circle, but so R is still in a sense useful, but we maybe need to think of other things. But and I have other questions I would ask, but we have people in front of me. Says Pavel wanted to ask a question. Pavel.
Yeah. So first of all, excellent talk. I'm in a few days I'm going to be talking about also bipartite networks, and it's going to be a tough act to follow. My thinking was actually along the same line as Deidre's question, was that sort of what kind of data one could get about that. And my sense is that one could actually piggyback on general social survey data by maybe getting using that to estimate sort of the global network features, and then trying to sort of calibrate the network model, unipartite or bipartite, to match those features. At least that's been my thinking. I don't know how do you think the framework you have could be amenable to that sort of calibration?
Yeah, yeah, I think it is, and I maybe wasn't clear. It was a little bit rushed, but so we do use commuting data for that to fit that propensity function, and then when I showed how you fit the distribution of commutes, there's no reason that the algorithm, the accept reject algorithm, could take any kind of pseudo likelihood. So you could explicitly impose the full commuting network for the UK as your you could make a likelihood out of that, so you could get as close to that as possible. So yeah, I think that's a really good idea. I think the difficult thing is like the number of contacts that really matter and the proportion of those that are random. So like how many people are going to get it from the tube. The proportion of people who are getting it from the tube is a key thing in any of these, and that's the more difficult thing to find, I think. I'm not sure.
And one more thing, it's a sort of trivial question. The screen you were sharing was very small, so the paper you just posted was Social Networks of Strong Spatial Embedding Generate Non-Standard Epidemic Dynamics Driven by Hierarchical Clustering. Is that the paper you were discussing?
Yeah, so that should be, it's on bioRxiv.
Yeah, okay, because I was watching it at a very low resolution, so I kind of,
Sorry, and just a very quick comment back to Dennis before Peter jumps in. I didn't talk about it today. We've done a deterministic approximation of how it maps onto wave dynamics as well. You can get the whole thing back to waves in households and between them, and there's some nice maths in there that, but I didn't go through it today.
That sounds fun. Was there one more question?
I think Peter was.
Well, I just posted something in the chat, so there is a way to define R, I would say, even if you have a purely spatial model, which is by seeing the fraction of the infection rate compared to the critical, what would be the critical infection rate. Of course, it's cheating, because finding that critical infection rate is very hard, but
we got a lot of computers now, so maybe that comes back to Adam's point, that's how we define it. And until we can do some really cool maths that Lorenzo might be interested in, then we just simulate the heck out of it, and that's what we work with. So yeah, thanks.
This definition, by the way, is not mine. It was suggested by Mark Hancock once.
Well, enjoy the credit in our preprint, and we'll correct it if we get the chance.
Right. Okay. What I was going